Well, hello. So this lecture, I'm going to finish up the last topic of Chapter 7, dealing with valence bond theory, and also go through the questions from your last midterm exam. And so valence bond theory, we already went through these definitions, but I just want to kind of remind you, it's been a few days. So it's dealing with a simple description of how do the electrons, how are they placed in orbitals that overlap between different atoms. And so if we have two atoms, let's say we're overlapping p orbitals, okay? Remember that, these are mathematical functions, so, one lobe is positive, the other is negative, and so they can overlap here and then share two electrons in that, okay? And so this is really just a very simple theory that talks about overlap of orbitals, okay? And the stronger the overlap, the stronger the bond, okay? And so we're going to talk today about a concept called hybridization. And this is something you're going to pick up on in organic chemistry, orgo, a whole lot, okay? And this just simply means mixing of atomic orbitals, okay? And you're going to form a certain hybrid orbital, okay? And so, for instance, if we look at methane, okay, we know that this is a nice stable molecule, okay? So its name is methane, natural gas, okay? We know that this is stable because, carbon has an octet. Okay, so that's happy. Hydrogen's surrounded by two electrons, so again, that's cool. But when we look at bonding, it's not really apparent. How is that possible? So this is the electronic configuration of carbon. Okay, it's 1s2, 2s2, 2p2. And so how can you overlap hydrogen with that? Okay, so hydrogen, remember, is just this. Okay, so it's 1s1, in other words. Okay, and so how can you form four bonds if you only have two electrons that are unpaired? Okay, and so, maybe if I do it this way, okay, where that's our 2s and then 2p, if I do it like that, and then so that's carbon, and then let's do hydrogen here. Okay, so if I change the color here, let's do red. Okay, this implies that I should really only be able to form two bonds, right? Because you've got one here, okay, so they'll pair up, okay, and when you pair it up, one electron, whoops, go back to black, then this will be spin down like that, okay, and then we can come in maybe with another hydrogen, okay, I'll show it up here, and I'll draw it like that purposely so that they will pair up, okay, and then you can form another one here. And so that kind of says that that is really all you'd be able to form. So how in the world can you get methane with four CH bonds? Okay, and so how or what happens is that you mix together S and P orbitals, okay? And so let me go back to black here. Okay, and so if you have this configuration, does everybody see if I move one electron, so let's say this one, if I move it into that empty orbital, okay, does everybody see that I'll have an excited state? Okay, this is really still the ground state configuration. So the lowest energy or most stable configuration for carbon is still that, okay? But when it's forming a bond, it actually makes sense energetically that this electron is promoted up, so now you've got this excited state configuration. Okay, and now I've got 4 unpaired electrons that can pair up with an appropriate electron from hydrogen. Okay, and to give me a CH4. Okay, and so since you're mixing together an S and 3 p orbitals, this is called the Sp3 Hybrid Orbital. Okay, so 3 p's and 1 s. Okay, and so that's shown here. Okay, so we have this ground state configuration. You move an electron here to this one. Okay, and now by Hund's rule, they're all parallel spins. Okay, and so now this is called an excited state configuration, and now you can form 4 bonds. Okay, it'll overlap with 4 electrons with opposite spins. Okay, so what happens is, if you were just to do this scenario, where hydrogen orbitals would overlap with, different p's, and then with an s, you would have different types of bonds, right? So, for instance, this might look like this, where you've got a hydrogen 1s that overlaps with a p on carbon. Okay, so that would be the 2p. Okay, so you'd have a certain bonding there, but then this one would look different, right? You, in that case, would be overlapping a 1s with hydrogen with the 2p or 2s of carbon. Okay, and so these would give rise to different types of overlap. And so, in other words, your bonds would not be equivalent. Okay, so your bonds would be different in that scenario. Okay? And so what happens is that you will mix together, okay, so as I said before, that you're going to mix together an S with 3 p's, okay, and what happens is you form these hybrid orbitals, okay, and so you move from this scenario where you've got, like 4 things that can overlap, and if you mix them all together, now you've got 4 orbitals with the same energy. Okay, and so now these are called Sp3 hybrid orbitals. Okay, and that gives rise now hydrogen can come in and overlap in here, and it's the same type of overlaps. You're going to have, we know that CH4, all of these bonds are the same. Okay, you don't have one that's longer than the other, in other words. And so you have to have a hybrid orbital, or electrons at that same energy level that are overlapping. Okay, and so hybridization is going from this excited state configuration where you're just mixing these together to form hybrid orbitals. Okay, and what they look like is these are the orbitals that you're mixing. Okay, so this is an S, and these are the 3 types of P's, okay, along the different axes. This is PZ, PX, and PY. And so if you mix them together, then you get Sp3, right? So these are, again, mathematical functions. So if you add this plus that, the purple or pink color here is positive. This is negative, the blue. And so if you add this and this, does everybody see you're going to end up with a lobe? So maybe I'll draw it like this. This plus that will equal like that. Okay, because these are both positive, that's negative. So you're going to end up with like a bigger lobe over here. Okay, and so this is your sp3 orbital. These are your really atomic orbitals. Okay, so when you mix them together, this sp3 has a lobe that is larger, and that means that they're pointed toward the atoms involved in that bond. So it's just that they become more effective at bonding these different atoms. Okay, and sp3, if you're going to mix this and then all of these together, they will point toward the corners of a tetrahedron. And we know that CH4, this molecule, is tetrahedral. Okay? Okay, so sp3, whenever you have something that is sp3 hybridized, then that means that it is tetrahedral in shape. Okay? So that's the first type. But we know, so that would be this example. Okay, so carbon with 4 bonds, so that's tetrahedral, sp3. But we know that carbon can also form this. Okay, where instead of carbon bonded to 4 things, it's only bonded to 3 atoms. Okay, and so in this case, it's not sp3 anymore. Okay, and so it's a different type of hybridized orbital, because now these angles, remember this is like our AX3 type of geometry, so these are about 120 degrees instead of 109.5. Okay, so it's a different shape, so it has to be different type of overlap. And so let's look at what happens there. Okay, so I guess this is just showing, overlaps. These are sp3s, and then your hydrogens just overlap along here. Okay, so that's for methane. All right, so now let's look at, going back to this example. I'll just move them over a little bit. Okay, so this again is our carbon. Okay, and we said that you can do this, form an excited state. So I'll say C star, okay, which is excited. And so you can mix all 4 of these. That will be sp3, okay, but you could also just mix 2 of these like that. Okay, so this is called an sp2 hybrid orbital. Okay, and you end up with a leftover p orbital. Okay, and what that looks like is, if we're looking at this bond, this bonding here, so between, we'll say, hydrogens, carbon, like that. Okay, so sp2 hybrid orbitals are trigonal planar in shape. Okay, so in other words, they're 120 degrees apart here. Okay, but carbon doesn't have an octet this way. So what happens is, these are all sp2 hybridized, and so you end up still with a leftover p on each of these carbons, and that can overlap to form a double bond. Okay, so this is the structure for ethylene. Okay, what we're saying is that these, if I maybe color these here, okay, this is your sp3, or sp2, sorry. So these are sp2 hybrid orbitals. This is formed from just p overlap, okay, between those carbons. Okay, so it's just, you have that empty p that can overlap, and that's where this double bond comes from. Okay, so so that's shown here, okay, where these are your sp2s, okay, that form a trigonal planar unit, and then you've got this leftover p orbital that can overlap. Okay, so sp2s, and then you've got a p, okay, and now to designate these different types of bonds, if you have something that is between these carbons, that's called a sigma bond. Okay, whoops, let's go back to black. Okay, so all these single bonds are sigmas, okay, because they are between the two atoms. Okay, and this one as well is sigma. When you have multiple bonds, that is formed from pi, or from p overlap. It's actually called a pi orbital. Okay, and so in this case, for this molecule, you would say that there are 1, 2, 3, 4, 5 sigma orbitals and 1 pi orbital. Okay, so a double bond counts as one of them is single, or one of them is sigma, and the other is pi. Okay. So in this case, if we had this molecule, then each of these, or I guess in that case, you would just have one sigma. Each of these ones would be pi, and that's also sigma. Okay, so a triple bond means you have one sigma, and then the rest are going to be pi's. Okay, so in this one we would have 3 sigma and 2 pi bonds. Okay, so let's look at this example where there's a triple bond. Okay, and again, if we look at that excited state, we'll just start from there. Okay, you can just overlap these. Okay, where that's your s and these are your p orbitals. You can just do an sp hybrid, and now you're left over with 2 p orbitals. Okay, and those are the ones that can overlap above and below that bond axis. Okay, so shown here, I don't know if that's, yeah, maybe this one. Okay, where you've got an sp orbital, which is linear. Okay, so this molecule is linear. And then you've got overlap, I guess, above and then kind of coming out at you. Okay, so these can also overlap kind of in this direction and in that direction, and those will form pi orbitals. Okay, and that's where your triple bond comes from. So your single bonds come from the green, okay, overlap of these green orbitals. Your double bonds come from this one, so that's 1, and that's your second. So that's why it's a triple bond. Okay, versus if we look back at just the double bond, you've got overlap here and then just one other. Okay. All right, so these are just the simple, there are other types of hybrid orbitals that are proposed you might see in organic chemistry with d orbitals. It's not really correct, but some chemistry textbooks say that d orbitals can hybridize as well. And so if you have sp hybridization, you will get a linear molecule. sp2, where you're overlapping an s and two p orbitals, that is going to be trigonal planar. And then sp3, we saw as our first case, was tetrahedral. Okay? And so a typical question might be this one, for instance. So you'll be given kind of a complex looking molecule like this. Like that. And then asked, how many sigma and how many pi bonds do you have in that molecule? Okay, is one type of question. Okay, and so literally it's this easy. So for sigmas, you're just adding up all the single bonds. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, and then pi will be going back to all the multiple bonds and then adding one of those. So in other words, this double bond, it has 1 sigma, 1 pi. Okay, if it's a triple bond, then it's a sigma and 2 pi's. Okay, and so that would be 9 sigma, 1 pi. Okay, that's it. Okay. The other question would be, this carbon, what is its hybridized, how is it hybridization? So what type of orbital is it? Is it an sp, sp2, or sp3? Okay, and here's the easy way to remember that, is whatever number this is, just look at how many atoms it's bonded to, and it will be always one more than what this number indicates. So in other words, CH4 was bonded to 4 atoms, right? The central carbon. So if it's bonded to 4 atoms, that means that it's sp3, or one less than this number. Okay, and so then if you look at this carbon here, it's bonded to 3, well, maybe circle them, 1, 2, 3 atoms. So that means it'll be sp2 hybridized. Okay, this one, it's only bonded to 2 other atoms, so that'll be sp. Okay, so basically, however many, just look at it as however many things are bonded to that atom, its hybridization is 1 less than that. As far as like the superscript on the P is 1 less than that. So if it's bonded to 4 things, it's sp3. 3 things, it's sp2. And 2 things, it's just sp. Okay? And so those are really the only questions you'll get are, what is its hybridization, or, how many sigmas or how many pi orbitals do you have? Okay, and in this case, you would have, I guess we already did this one, but you would have a total of 3 sigmas and 2 pi's. Okay? All right, so that is the rest of chapter 7. Okay, so now I want to change gears and go over, where is it? Right here. Okay, go over the topics or the questions on the last exam. Okay, so this is your midterm 3. Okay, and I guess, let me pull up a periodic table here. Actually, I'll do a proper one. Let's see. Yeah, maybe that one. Good old Wikipedia here. Okay. Okay, and so the first question is, what is the electronic configuration for zinc 2+? Okay, and so let's do just zinc by itself. Okay, so zinc is going to be argon, and then it's going to be 4s2, 3d10. Okay, and so if you're going to lose 2 electrons, remember that the s's leave first. Okay, so it's just going to be argon 3d10. Okay, so argon 3d10. Nitrogen. Okay, so the ground state of nitrogen, so it's going to be 1s2, 2s2, 2p3. And so the way that we put those 3 electrons in, according to Hund's rule, is parallel spins first. Okay. Beryllium difluoride. Okay, so beryllium has 2 valence electrons. Fluorine each has 7. So that's 14, so 16 valence electrons total. 1, 2, 3, 4, 10. Like that. Okay, and so this one is the proper Lewis structure. Okay, remember this is happy with, whoops, you can't see that. It's happy with less than 8 valence electrons. It's an exception to the octet rule. Okay. The Lewis structure for this one, so again, just counting up electrons. So we have 7 times 2 plus another 6, so 20 valence electrons. Do that so we have more space. So O. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 16, 17, 18, 19, 20. Okay, and then you see, does everything have an octet that should? And yep, that looks happy to me. Okay, so that is the proper Lewis structure. The best Lewis structure for SF4. Okay, so 7 times 4 is 28, and then another 6 for sulfur. So that is, what is that, 34, right? Valence electrons. So 8, 14, 6. 32, 33, 34. Okay, so something with a lone pair on the central sulfur. Okay, again, you know, in the midterm review on Monday, I said halogens do not form double bonds. Okay, so that's wrong. This one doesn't have the right number of electrons. You should have another 2 on there. Okay, so that's wrong. And then another double bonded one, okay? All right, electronegativity, just a definition. So it's just an atom attracting electrons to itself, okay? Ground state for cadmium. Okay, so let's go to the periodic table. So cadmium is element 48, so it's going to be krypton, and then it's going to be 5s2. Uh, 4d10. Yeah. Okay, so right here. Ground state configuration for F minus. Okay, so F minus, if you add one more electron to fluorine, you're going to get neon's configuration. So it's really 1s2, 2s2, 2p6. Okay, or that one. Selenium, configuration for that. Okay, so right here, so it's going to be argon's configuration, 4s2, 3d10, and then we have P4. So that's going to be 4p4. Okay, so this one looks similar, but you've got a 4d. Remember that it's 3d. It's always one less than the S and P that surround it. Okay. Number of valence electrons for ICl5. So they're all halogens, so it's really just 7 times 6, so 42 valence electrons. Okay. How many valence electrons do the halogens? So halogens are 7, so they're 1 less than the noble gases. The elements by decreasing radii size. Okay, so remember, the more negative you are, you're adding electrons, so that should be greater. Okay. This one, the more positive you are, you're taking away electrons. So it should be smaller and smaller, so that one should be like that. Cations are always smaller than their atoms, and so this is correct because you've added 3 electrons to nitrogen, and so that one is wrong. Okay, the other way around. Strongest bond, so a triple is going to be stronger than a single. Okay, you've just got more electrons between them. So you've got 6 electrons versus only 2. Okay. Does it have a formal charge of +2? Okay, so just kind of looking at these alternatives. So the middle atom, here you've got 6 minus 4 bonds, so that's +2. Okay, so I guess, you know, you're there as far as the answer. But looking at these others, this formal charge would be 2 minus 2 bonds, no dots around it, so that's just a 0 charge. This one would be 6 minus 6 bonds, so that's also a 0 charge. This one would be 3 minus 4 bonds, so that actually would be a -1 charge. And then this, the central atom, would be 6 minus 3 bonds, and then another 2 dots, so that's a +1. Okay, so the only one with a charge of +2 is this one. Okay. Decreasing first ionization energy. Okay, and so the trend here is it will go up as you go left to right. So anything with a noble gas, that's going to be the highest ionization energy. Okay, and so I guess just looking at this, you could tell right away that that's got to be correct. Okay, it's going to be bigger than anything. And so then moving on between magnesium and cesium, then, so you've got magnesium here, cesium way down here. Okay, and so as you go down a group, the ionization energy will get lower. Okay, and so cesium's down here, and magnesium is up here. Okay, and so that's why cesium is the least, and magnesium is more than that, but it's still less than the noble gas. Okay, so that's this order. There we go. Okay, so this order here. The shortest wavelength, okay, means the highest energy. Okay, so gamma is going to be more intense than UV. Whoops, and we lost connection. There we go. Okay, so gamma is going to be greater than UV, which is greater than IR, and radio is the lowest energy. Okay. Calculation. Okay, so it's 99.1 megahertz find the wavelength. Okay, so here, so wavelength is c over frequency. Okay, and so that is 3 times 10 to the 8th meters per second divided by frequency, and so that is 99.1 megahertz. So that is 99.1 times 10 to the 6th hertz, or we can say, seconds to the -1, so these units cancel. Okay, so I know that that's not proper scientific notation, but it kind of helps knowing that a mega is 10 to the 6th of the base unit. Okay, you've got kilo and then mega. And so it's just a factor of 10 to the 6th. Okay, so then if you plug that in the calculator, 3e to the 8th divided by 99.1 e to the 6th. Okay, we lost connection again for some reason. There we go. Okay, so if you do that math, you end up with 3.03 meters. Okay. Lewis structure for CS2, carbon disulphide. So we've got 4 for carbon plus 6 times 2. Okay, so 16 valence electrons. And so this is going to be analogous, whoops, I even did it, to carbon dioxide. Okay, because sulfur's in the same group as oxygen. Okay, and so we have to place 16 electrons. So you have 1, 2, 3, 4, 9, 10, 11, 12, 13, 14, 15, 16. And then you notice that carbon doesn't have an octet, so you have to do that. And then that. Okay, so it's this structure. Formal charge for chlorine. Okay, so that one, it's just 7 minus 1, 2, 3, 4, 5, 6 bonds, and then you don't have any dots around it, so it's just +1. Number of resonance structures for nitrate ion. Okay, and I guess we did this in final review, but nitrate is NO3 minus. Okay, and so that has how many? 26 valence electrons, right? 18. No, 18. 24. Whoops, sorry. 24 valence electrons. Okay, so you can draw it like this. So 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12. 24. Okay, and then you notice nitrogen doesn't have an octet, so you can do that. Okay, and then as far as formal charges, you can do a little bit better and maybe do that. Okay, and so now the formal charge of that one is 0, that one's 0, and that one is minus, and this is also 0, right? 5 minus 1, 2, 3, 4, 5 bonds. Okay, and so you have structures then with 2 double bonds in them, so you can draw a resonance where maybe the doubles are like this, okay, or like this. Okay, so you're just moving around the position of the double bonds, and there are 3 varieties that you can use or draw. Okay. Solar radiation. So this one, energy of a photon. So E is equal to, this is with wavelength, hc over lambda. Okay, and so you plug that in. Times 10 to the minus 34 joule seconds times speed of light. meters per second. Okay, and then divided by the wavelength, so 500 nanometers. So again, if you do that, okay, not scientific notation, but 500 times 10 to the minus 9 of a meter, okay? Then that way you don't mess it up as far as converting it wrong. So then you just do that, 6.63 e to the minus 34 times 3e to the 8th, and then divide that by 500 e to the 9 minus. You get 4 times 10 to the minus 19, and joules is the unit here. Okay, everything cancels except joules. Ionic character, okay, so silicon, and then you're comparing it phosphorus, sulfur, or chlorine. So phosphorus, sulfur, chlorine, okay, and so the one that there's the biggest difference in electronegativity is silicon with chlorine, and so that's going to be the most ionic, followed by sulfur, followed by phosphorus. Okay, so this one. Okay, so again, silicon, chlorine is the biggest difference in electronegativity. So it will be the most ionic. And then you've got silicon sulfur and then silicon phosphorus. Okay. The orbitals for n equals 3. Okay, so for an n equals 3, that means that L can have values of 0, 1, and 2. Okay, or in other words, S, P, or D orbitals. Okay. Oops. Okay, so I guess you couldn't see that, but yeah. Remember, L's can take values all the way to n minus 1. Okay, so you've got 3 values for L, and these are what those different quantum numbers for L mean as far as orbitals. So you've got an S, P, and D. The distance between identical points on successive waves. Okay, so this to that, or that to that. Okay, those are wavelengths. Okay, really, as far as definition, it's really between successive crests or troughs. So between there, okay, so this is a wavelength and that's a wavelength. Okay. And what's the wavelength having a certain frequency? So it's C over frequency. So it's just 3 times 10 to the 8th meters per second divided by 4.8 times 10 to the 14th seconds to the minus 1. Okay, and you end up with 3, so 3e to the 8th divided by 4.8 e to the 14. So that's 6.25 times 10 to the minus 7 meters, okay, or 630, really, 625 nanometers. Okay. What's wrong with this Lewis structure? Okay, so too few electrons. So let's see how many electrons you should have. So you have 1 from the hydrogen, 4 for carbon, 7, and then 6. So you should have 18 electrons total. And so if you look, you've got 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So it can't be that, or too many electrons. Carbon has an octet. So really it's between, there's either nothing wrong with it or oxygen doesn't have an octet. And so you look, and yeah, oxygen only has 6 electrons. So that's the right answer. Okay. Covalent bonding, so just a definition, so two nonmetals, okay? So this would be ionic. If you have two metals, that's really just metallic bonding. A metal and a noble gas really would be, that's a tough one. That's probably going to be more ionic than anything. I don't know, are there, I guess I've never seen examples of that, so I don't know if there are any examples of a metal with a noble gas. All the compounds with gases are, for instance, this one, okay, where it's a non-metal, okay? So I don't think that even exists. And an actinide, it's not bonded with anything, so there's no bonding, so it doesn't even make sense, okay? The Lewis structure for Br minus, and so you're just, putting 8 electrons around it and indicating its charge. Okay, so Br has 7 valence electrons, so Br minus would have 8. Okay. Definitely incorrect. Okay, so PCl5, phosphorus can expand its octet, so everything looks good there. NO2 minus, you're looking at number of electrons. So you should have 12 plus 5 and then another 1 there. So it's 18 electrons. So let's count 2, 3, 4, 5, 6, 7, 8, 9, 10, 16, 17, 18. So that's cool. Nitrogen has an octet, so that's good. All the oxygens have octets, so that's fine. SO3 2 minus. There you should have 26 valence electrons. So we have 2, 3, 4, 5, 6, 7, 8, 9, 10, 22, 23, 24, 25, 26. That looks good. Sulfur has more than an octet, but it can, so it's good. All the oxygens have octets. So again, that looks good. This one, even without counting electrons, you can tell there's no octet, right? So you know that that's wrong. Okay, and then this one is an odd number, so you've got 6 electrons and 5, so there's only 11 valence electrons, and so you're going to have an odd number somewhere, right? And so this is kind of one possibility. You could draw the one where you've got a dot over here. Okay, but with the other varieties, okay, but so I guess, yeah, so let's do it properly. So you could draw it, so with 11 electrons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, okay, and then maybe do a double bond in there. So you could have that, for instance, so either of these maybe are possibilities, but this one is definitely wrong because you don't have an octet on carbon, which is most likely to be ionic, so just look for metal and non-metal. Okay, so that's the only one. And then electron affinity, so it's just adding an electron to something, so this is just a definition type of question. Okay, this is ionization energy, okay, where you're kicking off an electron. Okay, and this would be in an affinity as well, but it's not the electron affinity of sulfur. Okay, so that's of S minus. Okay, and that's the last question. All right, so let me know if you have any other questions. Take care. Bye.